And now we have the last part of our discussion on atomic and nuclear physics. Examples part 3, wherein we look at 4 more examples or 4 more sample problems. Example 8. Find the longest and shortest wavelengths in the Lyman series. The Lyman series is given by 1 over lambda is equal to r times 1 over 1 squared minus 1 over n squared, where n is equal to 2, 3, 4, 5, 6, and so on. For n, we can see that the smallest value of n smallest value of n is 2, and the highest value of n may be considered to be infinite. Since lambda depends on n, we calculate the wavelength lambda for the smallest value of n and for the largest value of n. For the smallest value of n is equal to 2. You have 1 over lambda is equal to r times 1 over 1 squared minus 1 over 2 squared. We are able to calculate lambda 2, 1.215436038 times 10 to the negative 7 meters. For the largest value of n is equal to infinite. 1 over lambda is equal to r times 1 over 1 squared minus 0. 1 over infinite squared is equivalent basically to 0, which will give us lambda infinite is equal to 9.115770283 times 10 to the negative 8 meters. Comparing lambda 2 and lambda infinite rather, lambda 2 is larger than lambda infinite, which means for the Lyman series, the longest wavelength is lambda 2, 121.544 nanometers, and the shortest wavelength is lambda infinite, 91.158 nanometers. Moving on to the next example, example 9. You are given the following neutral atomic masses. You have atomic mass of radium, 226.025403 U. And then you have radon, 222.017571 U. Show that the calculated kinetic energy of the emitted alpha particle agree with the experimentally measured value of 4.87 mega electron volts in the alpha decay of radium. So the radium decays into radon. The alpha particle emitted has a kinetic energy of 4.87 mega electron volts experimentally. Radium will decay into radon and alpha particle. If we look at the masses, mass of radium is given 226.025403 U, whereas the mass of radon is 222.017571 U. Mass of the alpha particle we know to be 4.002603 U. If you compare, mass of radium will decay into radon and alpha particle. If you compare the masses, mRn, m radon plus m alpha particle is less than mass of the radium. There is extra mass. That extra mass is converted into the kinetic energy of the alpha particle. So first, we take the extra mass, the original mass of the radium, and then you have the combined mass of radon and alpha particle. Get the difference? You have m extra is equal to 5.229 times 10 to the negative 3 U. Converting this into energy, you have kinetic energy of the alpha particle 4.871 mega electron volts. Moving on to the next example, example 10. The radioactive isotope cobalt 57 decays by electron capture with a half-life of 272 days. Find the decay constant and the lifetime. If you have a radiation source containing cobalt 57 with activity 2.00 microcurie, how many radioactive nuclei does it contain? So given half-life, T1 half, 272 days, or 2.35 times 10 to the 7 power seconds. The decay rate or the activity is given at 2.00 microcurie or 2.00 times 10 to the negative 6 curie. This is equivalent to 7.40 times 10 to the 4th power decays per second. The lifetime is equal to half-life divided by ln of 2. Knowing T1 half, knowing the half-life, we are able to calculate the lifetime. 33.903 times 10 to the 3rd power seconds. The decay constant is just 1 over the lifetime, 1 over T mean. Knowing T mean, knowing the lifetime which we have just calculated, we are able to calculate the decay constant, 2.950 times 10 to the negative 8 per second. Now, activity is just equal to the decay constant times n, the number of nuclei in the sample. N is just equal to the activity divided by the decay constant. Knowing the activity and knowing the decay constant, which we have just calculated, we are able to calculate the number of radioactive nuclei that the sample contains. N is equal to 2.509 times 10 to the 12th power nuclei. And lastly, we have the following problem. Example 11. Before 1900, the activity per mass of atmospheric carbon due to the presence of carbon-14 averaged at about 0.255 becquerel per gram of carbon. In analyzing an archaeological specimen containing 500 milligrams of carbon, you observe 174 decays in 1 hour. What is the age of the specimen, assuming that its activity per mass of carbon when it died was that average value mentioned for the air? Let the half-life of carbon-14 be 5,730 years. So half-life of carbon-14, 5,730 years. That's around 1.808 times 10 to the 11 power seconds. Mass of the sample is given 500. Mass of the specimen is given 500 milligrams or 0.5 grams. For the average value of the activity given before 1900, the average value of the activity is 0.255 becquerel per gram. We have 500 milligrams or 0.5 grams of carbon. We are able to get the activity 0.255 becquerel per gram times 0.5 grams. That will give us 0.1275 decays per second. So this is the activity before the 1900. The decay constant is just given by ln of 2 divided by the lifetime. We are able to calculate the decay constant to be 3.833778654 times 10 to the negative 12 per second. This is the decay constant when the specimen died, when the sample died. N is just equal to the activity divided by the decay constant. We are knowing the decay constant when the sample died and knowing the activity rather when the sample died and knowing the decay constant when the sample died. We are able to calculate the number of atoms when the sample died. 3.325700608 times 10 to the 10 power atoms. So this is the number of carbon-14 atoms when the sample died. In terms of determining the age of the sample, determining when the sample died, this will be our starting number for the number of atoms. So at present time, let the initial number, the original number of the atoms be equal to the n that we calculated, 3.325700608 times 10 to the 10 power atoms. At present time, the decay rate is given by the problem. When the sample died, when studying the sample rather, we observe 174 decays in 1 hour. So at present time, the decay rate is given by 174 decays per hour or 0.0483333 and so on decays per second. And again, the number of atoms is just equal to the decay rate divided by the decay constant. The decay constant, we already know, 3.833778654 times 10 to the negative 12. If you recall, that's what we calculated for the decay constant for carbon 14. Knowing the decay rate and the decay constant, we are able to calculate the current number of atoms, 1.260723106 times 10 to the 10 power atoms. The original number of atoms N naught and the current number of atoms are related by N is equal to N naught e to the negative lambda t. Isolating t, we are able to calculate the age of the sample. 2.504 times 10 to the 11 power seconds, roughly 8,000 years. And that's it for our discussion on atomic and nuclear physics. So thank you for watching.